Hello. For today's lab, I will discuss the physics of a soccer kick. The purpose of my lab was to model the motion of a spinning soccer ball after it has been kicked using Newton's second law. The forces that I applied to my motion in Newton's second law were the force of gravity, the force of drag, and the Magnus force, which you can see right here in my results. The Magnus force, for those unfamiliar with it, is due to the spinning motion of a ball. My results are that the observed motion fit pretty well with my model. The red line is my model. The green dots is the observed motion, and the blue line is my model without including the Magnus force to show what an effect the Magnus force creates. The only discrepancy is that my model predicted the ball to hit the ground, which is in this graph, the representation of the ground is the x-axis. The physics principle that I used for this lab was Newton's second law, where the net force included the gravity, the Magnus force, and the drag force, as I said earlier. The force of gravity, which is easy to calculate, is just mg. The force of drag is proportional to the square of the velocity, and in my code I included this whole first part of the equation as the constant, so I didn't have to worry about calculating each of these separately. The Magnus force is similar to the drag force, but this side of the equation is proportional to the angular velocity of the ball times the velocity of the ball. So the angular velocity relates to the spinning motion of the ball. Also in my code, I included this whole left side of the equation in one constant to simplify the code. Here's how I analyze my motion in Tracker. This is the initial kick of the ball, and from this I was able to get results that I could compare to the model that I'd eventually get. And also from this, I was able to calculate the initial velocity using the first two positions of the ball as it moved. The second footage that I used was to calculate the angular velocity of the ball. Using a slow motion camera placed right in front of the kick, I was able to see how many times the ball spun in a certain amount of time. And using that, I calculated the angular velocity of the ball in radians per second. The last clip that I used was this video of me dropping the ball. From this, I was able to calculate the drag constant for the motion, which then I applied to the full model of the entire ball looping through the air. Here's the specifics of my calculations. To get the initial velocity, I used the change in the distance over the change in time for each axis, so one for the y-axis and one for the x. Here's an example that I used for the x-axis. The change in position over the change in time equaled 6.088 meters per second, but that was after at the second point of measurement. So to calculate the initial velocity, I used Newton's second law, solving for the initial y velocity, where I had the mass times gravity as the one force and the force of drag. I didn't include the spin force, the Magnus force in this, because I couldn't yet calculate the constant for that, but this was a good enough approximation for it. And so using this, I was able to solve for the initial y velocity, and I did the same thing for the x, except I didn't include the gravity force in that. And to calculate my angular momentum, I used 2 pi, which was the amount of the full rotation, so the full circle of the ball, divided by the amount of time it took for it to do. And this was an average of 0.166. The average of the time it took for the ball to make 3 separate circles, and that's how I calculated my angular velocity. Now let me take you to my code. I put in the ball's mass, which was 0.405 meters. I put in the ball's initial position, which I had at the origin of my coordinate system, the initial velocity, which I showed you how I calculated that just now. I put in all the constants, the 37.85, the angular velocity, g, the b, which was the drag constant, and c, which was the proportionality constant for the Magnus force, which was the whole left side of that equation that I showed you at the beginning of the video. So in the loop, I've got the weight force, the drag force, which is the negative b times the square of the velocity. It's negative because it's always opposite to the direction of the velocity, and the Magnus force, which is that left side of the equation, which I had at c, times the angular velocity times the ball's velocity. And then I used the net force to predict the motion each time it went through. So let's see how it's predicted. As you can see, it looks it looks a lot like our motion, except that it goes past the point where the ground is, because I have the time step equal to the same amount of time that the actual observed motion took place. And if it goes past the ground and has nothing to stop it, of course the force of gravity will just keep it going down at a higher and higher rate. Now let's take a closer look at the results. As you can see, and as I showed you at the beginning, the model and my observed motion matched pretty well, but the model predicted the ball to hit the ground a couple of tenths of a second earlier than the observed motion hit the ground. The Magnus constant that I used for the model was calculated experimentally when trying different values and comparing them to the observed results, which was the same way I calculated the drag constant. The results weren't perfect, however, due to a number of possible reasons. One, it was somewhat windy in the air and the ball was high, so the drag could have been variable, so it wouldn't have been constant the whole time and maybe caused the ball to stay in the air a bit longer than it would have if the air had been still. Another possibility is that there was right and left spinning of the ball, although I tried to control for this by creating it an only two-dimensional model and having various attempts at kicking it to get the ball to spin as straight upwards as I could make it go without any tilting to the side. But any minimal spin to the side could have also affected the results differently and caused the ball to move differently when looking at it from this direction. But for the purposes of this experiment, the results were solid. In conclusion, we can see that the Magnus force, or the spinning force that is applied to a soccer ball when you kick it, can greatly affect the trajectory of the motion, which I finally show in this comparison graph of the ball without the Magnus force and the ball with the Magnus force. The upwards spinning of the ball can cause it to float in the air much longer than it would have otherwise without a spinning motion. Thank you, and that's my lab.